So, hello everyone, how are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics. I'm Aman, just welcoming you all to a new amazing video in which we are gonna be proving this identity down in this video actually. And you know what? Like this, we did use of this identity in the proof of this one actually. And this one was the Euler's integral representation of the hypergeometric function. And it was my last video, right? So I promised you guys that I'm just gonna prove this one down. And here with that. So let's just talk about the proof. And it's pretty easy. It's not that difficult to prove this down, but yeah, it's fine, and let's just talk about the proof. Okay, so basically we have to prove this thing down. So it's 1 minus x to the minus a, and it's an identity, it's a binomial, generalized binomial theorem, we can say. It's the sum as n goes from 0 to infinity of the Pochamer symbol of a sub n over n factorial times x to the n. So that's what we are gonna prove in this video. And yeah, believe me, this identity played a crucial role in the proof of this Euler's integral representation of the hypergeometric function. So I hope you have watched that video, and if you have watched that video, so you know like how important this one was. So it's extremely important to prove this down. So let's just talk about the proof. So uh, let let's just play with around. Let's just play around with you can say a power series, right? Power series of the function. So let's the power series as n goes from one. I'm sorry, 0 to infinity of a sub n. So this is the coefficient and which we have to evaluate in this video, and that's gonna be equal to this thing, right? So that's what we're gonna prove in this video. And a sub n times x to the n. So if we talk about the derivative of this very equation, so it's d over dx of 1 minus x to the negative a equals d over dx of this infinite sum as n goes from 0 to infinity of a sub n times x to the n. Okay, and so that's going to be giving us, if we talk about the derivative, so it's going to be negative a, and with the chain rule inside this parenthesis we're going to have a negative in front, and we would be having 1 minus x to the minus a minus 1. So that's this negative and this negative are going to just neutralize with each other, so we would be having a times 1 minus x to the minus a minus 1, right? So that's what I have written over here. So yeah, and if we talk about the right hand side, so since this a sub n and this sum is not depending on x, so we have to just deal with the thing that depending on x. So if we talk about the derivative of x to the n, so it's n times x to the n minus 1, right? So that's what we have written over there. Okay, and now okay, we can write this thing as a over 1 minus x. Actually, I have just used this negative exponent, right? And 1 minus x to the 1 minus x whole to the negative a as it is. And on the right hand side, we just have written the same thing that we had earlier. And next, you know what? Guess what? So this thing, this very function, we had assumed it to be this sum. So that's what I've done. Actually, I have replaced this function with this sum here. So yeah, so it's a times this sum, right? The sum as n goes from 0 to infinity, the power series actually, and this was our function. So a sub n times x to the n. And simultaneously, I have multiplied both sides with 1 minus x. So here we are having 1 minus x times the sum as n goes from 0 to infinity of n times a sub n times x to the n minus 1. Okay, so basically I'm just going to multiply the sum to this 1 and to this x as well. So that's going to be giving us a times sum as n goes from 0 to infinity of a sub n times x to the n equals the sum as n goes from 1 to infinity. Wait a second, like we are having n equals 0, and how did I write here 1? Actually, you know what, when we talk about this argument. So when you plug n equals 0, so since n is 0, so everything is 0. So basically the first term of this sum is going to be 0. So that's why we can write this as from n equals 1. So n equals 1 to infinity of n times a sub n times x to the n minus 1, when this is being multiplied to 1. And if we talk about when this sum is being multiplied to minus x, so that's going to be giving us, well, x times x minus 1, it's going to be x to the n, right? And here we are having the negative in front. So sum as n goes from 1 to infinity of n times a sub n times x to the n, right? So basically, our next step for this sum is let k equals n minus 1, just changing the index variable. So yeah, and here we can say n is k plus 1, right? So when n is 1, when you plug n equals 1 here, so 1 minus 1 is 0, right? So basically k is gonna be beginning from 0. And guess what? Since the first term of, like, look, wait a second. The first term of this, oh, wait a second, actually, the first term of this thing can be 0, right? Basically, if here we are having n equals 1, and here I have written n equals 0. So when we plug n equals 0 back over here, so the first term is 0. So basically, this sum is going to be n equals, like, beginning from n equals 1 only, specifically. So it doesn't gonna bother us if we write it from n equals 0, right? So the sum as k goes from 0 to infinity of k plus 1, actually, when n is being replaced with k plus 1. Check this out. So n is being replaced with k plus 1, and n is also being replaced with k plus 1, and n minus 1 is k, right? And on the left hand side, we are just moving upward, like we're just moving with that thing only, and minus the sum as n goes from 0 to infinity of n times a sub n times x to the n. Okay, and since this k is just the index variable, so we can just plug this back n, so that's not going to bother us, because eventually when we evaluate the sum, so we would be having, we would not be having anything in terms of n, because n is going to vanish, right? So that's why. So this sum, I have just multiplied this a into this coefficient. So this sum as n goes from 0 to infinity of a times a sub n, actually small a times capital A sub n times x to the n, and times equals the sum as n goes from 0 to infinity of, actually I have just factored out this sum and this x to the n as well. So it's going to be n plus 1 times capital A sub n plus 1 minus n times capital A sub n, and times x to the n. And guess what? We are having this sum, and we are having the x to the n over here, and again sum and x to the n. So basically, we can say the coefficients of x to the n, this one is equal to this one, right? So basically, the comparing the coefficients of x to the n, so we would be having small a times capital A sub n equals n times, I'm sorry, n plus 1 times capital A sub n plus 1 minus n times capital A sub n. And from here, adding both sides with this n times capital A sub n. So that's going to be giving us a plus, I'm sorry, a times capital A sub n plus n times capital A sub n equals n plus 1 times a sub, actually capital A plus, I'm sorry, capital A sub n plus 1. And here we can factor out this a sub n, right? Because that's common, and simultaneously we can divide both sides with n plus 1. So that's going to be, that's going to giving us a plus n over n plus 1 times a sub n equals a sub n plus 1. And here we are done with the very important thing. And now we already have a naught, actually a0 is 1. And why a0 is 1? So let's just talk about this a little bit here, guys. So basically, when your like, look, when you plug n equals 0, so it's gonna be the first term is a naught, right? Actually a is 0, and e is 0, right? So basically it's not depending on x, so that's why the first term is gonna be 1. And if we talk about here, so basically, like, look, obviously I need to mention this down, that the wait a second, the absolute value of x should be less than 1, right? So okay, So from this very equation we can say that a naught is 1, and we need to go for a1, a2 and a3, right? And yeah, okay, so let's just get back to that. Okay, so we have a naught is 1, and when we plug n equals 0 in this equation, in this very equation, so it's gonna be a over 2. Wait a second, I think it's not 2 because n is 0, so it's a over 1, right? And it's, wait a second guys, wait a second. Oh, I'm sorry guys. Actually, I just messed up here. It's not 2, and I need to fix this down. Let me just fix this down, guys. Wait a second. Just wait. Let me just explain it to you like in detail. Wait a second. Let me just erase all the things here, and then we'll talk about the things. So we have a naught equals 1, and actually if you are not still able to understand why a naught equals 1, so basically here we are having like when if we talk about this one, so basically x is 0, right? When we talk about a naught, right? So basically like the first term is a naught, and here your x is, so basically it's gonna be, yeah, I hope you all are getting that. And okay, just wait a second. Actually, yeah. So your first term is gonna be 0 here. So a naught is gonna be 1, right? So when you plug x equals 0, so a naught is gonna be 1. So yeah, that's the reason actually. Okay. So now let's just talk about this. So let me just write all the things down for you. So we have a naught equals 1. So when n is 0, right? So it's gonna be a plus 0 over 1. Actually, not 0. I'm so sorry. I need to fix this down. And equals a, actually a naught equals a1. So from here you can say a1 equals a over 1 factorial you can say. And when we talk about n equals 1, so it's gonna be a plus 1 over 2, and it's a1 equals a2. So if we plug this back like this, a1 over here, so that's gonna be giving us a times a plus 1 over 2 factorial. Actually 2 times 1 factorial is just 2 factorial. And if we talk about this, it's the recurrence, right? So if we talk about n equals 2, so it's a plus 2 over 3, and a2, wait a second, yeah, a2 equals, and equals a3, right? So such that a3 is gonna be, when we plug a2 back over here, so that's gonna be giving us again, it's a times a plus 1 times a plus 2 over 3 times 2 factorial is just 3 factorial. Okay, and now introducing the Pochamor symbol, and we did use of this thing as well in our previous video. So it's this representation. It's the gamma of a plus n over gamma of a. And guess what? This is the Pochamor symbol's representation, right? So basically, if we talk about the generalization of a sub n after this, following the recurrence, this pattern, so that's going to be giving us a times a plus 1 times a plus 2, and dot 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 all the way up to a plus n minus 1 over n factorial. And from our Pochamor symbol's definition, we can say that this is the thing that represents Pochamor symbol, and hence we can say our a sub n equals the Pochamor symbol of a sub n over n factorial. So yeah, that was the actual proof of this thing. And again, guys, if you got to learn something out of it, please make sure to like, subscribe, and share. And if you have any doubts so far, you are free to ask me in the comment section. I'll be there to reply over your questions. Thank you for watching this video, guys. Goodbye. Take care. Love you. And just learn mathematics, study mathematics, and just uh, love mathematics and love your life as well. Don't forget to love your life because it's extremely important. Okay. Goodbye, guys. Take care. Love you. And let's just get back to the next video.